In section 3.4, differential equations with complex eigenvalues are considered. Okay, so in this short video, I'm just going to talk about why complex values appear and just the situation in which that you would expect that to happen. Okay, so the thing to recall, okay, is that we spent a little bit of time discussing the second order differential equation that looked like this. This is what we call the mass spring differential equation. M is the mass on a spring, the mass of the mass on a spring. B is related to how much friction is built into the mass spring system, and K is essentially a number that relates to the stiffness of the spring. Okay, so if in the simple case that you let the differential equation M and the differential equation be 1, you let the damping, there be no damping, so B is 0, and then just let the stiffness of the spring be equal to 1 for simplicity. Your differential equation, second order for the mass spring system, becomes y double prime plus y equal to 0. Okay, which we knew we could turn to a system, systematize, if that's a word. You can make that into a system by letting y dot equal to v, and therefore y double dot is v dot plus y equal to 0. And the best way to do this would be to solve for the derivative variables. So v dot is equal to negative y. Okay. So as a system, right, the mass spring system can be written as dy dt is equal to ay, where y is the position variable, y is the position of the mass on a spring, position of the mass, and v is the velocity. Okay, and therefore the matrix A would be 0, 1, negative 1, 0. Okay. So this matrix right here evidently will have complex eigenvalues, right? And it's the complex eigenvalues that occur when you're looking at a mass spring damper system, usually. Okay, so take a look at what's going to happen in this case. When you set the mass to be 1, the damping to be B0, and the spring stiffness to be 1 by setting these parameters here. And then you pick your initial condition in the phase plane, right? So let's assume that you set the 0 velocity. You don't want to give it a push, but you compress the spring a bit, get it going. And you can see here that your position looks like it's going to be over here in the time plot, some sort of cosine kind of graph, because it started up here. So this looks like some sort of cosine graph. And in the phase plane, you have a circle. Okay. So what we're going to see is complex systems of differential equations with complex eigenvalues. You have the equilibrium 0, 0 here. And then your solutions are the circles, depending on where you pick your initial condition. Right? So if you pick another initial condition over here, circle, circle, all these are related to the mass spring problem with no damping. Okay? So we get all these circles in the phase plane in the position and velocity phase plane. Okay? So a new word that will appear in this section is that when you have complex eigenvalues and you get circles in the phase plane, that indicates that 0, 0 is what is called a center. Okay? So this is the context in which we have to consider complex eigenvalues because they occur in the very special and important case of a mass on a spring. Okay, so anytime you have a mass on a spring, you will have complex eigenvalues. Even if you put in damping in the problem, right, in which case your solution won't oscillate forever, but it will die out. Even in this case, you will have complex eigenvalues. Okay, so that's what needs to be discussed in section 3.4, the notion of complex eigenvalues.